Hello class, I can't be in class this week, so I'm making you a recording of what we would have covered during class. So we're moving on to Chapter 7, and we're going to learn about linear regression. And last week, remember, we learned about correlation, and this week we're moving on to regression. So let's take a look at this picture here. They explored the relationship between the protein in products at Burger King and the amount of fat. And they did a scatter plot, and the correlation coefficient we notice here is a positive direction, fairly strong. Doesn't look like there's a lot of unusual data values. And this indicates a strong linear fit, but what's the line that best fits the data? And that's what we're going to talk about in Chapter 7. That line should be closest to the points. Now if we notice, the points are not on a straight line, so we need to figure out a way to fit the line. And one thing to think about, if this red line were the correct line that we were going to use to explain this data, to describe it, if you notice, the points don't all fall on the line. So the distance between the actual value and the predicted value, which we're going to call y hat, is called the residual. So we can call it data minus model, actual minus predicted. And the residuals are what we use to actually gauge the fit of the line. And so the residuals are going to drive how the fitting gets done when we do it mathematically. So the residual is the difference between the observed value, the observed being the y value, not the x value, because when we build the regression equation, we're going to use the x values to predict the y values. And another thing to talk about with residuals, if the point is above the line, then that means it's a positive residual, and it means that the line is underestimating. And if the points are below the line, those are going to have negative residuals, because again, remember the residual is calculated as the observed minus the predicted, then the line is overestimating, or the model. The line gives, in this case, gives us the average fat content expected for a given amount of protein. The best fitting line will have small residuals. And again, you're going to use StatCrunch to do this, to do the fitting process. High negative residuals are just as bad as high positive residuals, and the line's going to be fitted so that the sum of the residuals is actually 0. But we're going to fit it based on the square of the residuals. So the line of best fit is the line for which the sum of the squares of the residuals is the smallest, and actually it's given the name the least squares line. And from algebra, remember the line, slope-intercept form, y equals mx plus b. The line of best fit for regression is changed around a little bit. We flip the order and we put beta naught first, that's the y-intercept, and then we put the slope term, beta 1, times the x value. So beta 1 is the slope. It tells us how rapidly the predicted y is changing with respect to x. And again, beta naught is the y-intercept. This is the value of the predicted y when x is equal to 0. So it goes back to the protein example. So here's the line of best fit. Y hat, what we're trying to predict, which is fat, is 8.4 plus 0.91 times the protein. So the slope tells us that a Burger King item with 1 more gram of protein is expected to have 0.91 additional grams of fat. Remember, slope is the rate of change. The y-intercept, this is a Burger King item with no grams of protein. It would have 8.4 grams of fat. In reality, the 2 items with no protein also have no fat. Okay, here's another example. This is a model for hurricanes. And if we look at the scatter plot, we notice a negative direction, pretty strong relationship, and it's linear. Here's the equation that fits the model, so that we're predicting the maximum wind speed is y, and there's the y-intercept, and there's the slope. And it tells us that for every millibar increase in central pressure, we can expect a 0.897 decrease in the maximum wind speed. The y-intercept tells us what happens when we have no central pressure, but that can't happen, so that doesn't really have any meaning in the context of the problem. And in fact, if you notice here, the axis was cut off. It doesn't go all the way down to 0. So here's some formulas. I'm not going to have you worry about them. What I did want to point out, though, is that the slope is related to the correlation coefficient. And in fact, the sign of the slope is going to be the same as the sign of the correlation coefficient. So if the correlation is positive, the slope will be positive, which makes sense. If the slope is negative, the correlation will be negative. And remember, the correlation had no units, but the slope has units of the units of y over the units of x. So So for the Burger King example, the units for the slope would be grams of fat, what we were trying to predict, per grams of protein. The y-intercept and the slope are related by this equation. Again, you don't need to know these, but I just wanted to show you that we can use the mean of the y's and the x's to create parts of the regression equation. And in fact, the regression equation goes through the point x bar, y bar. That really kind of anchors the fitted line on the graph, and then it's rotated in order to minimize the sum of the squares of the residuals. So again, that x bar, y bar will always lie on the line of best fit. So fitting it with technology. The formulas are useful to see the relationships, but we're always going to use technology. So for computations, you always use a computer, and we're going to use, it's in your StatCrunch program, you use, go to Stat, Regression, and a simple linear regression. And in a minute, I'll do some examples for you. So you can also predict, once you've built the line of best fit, calculated it, you can do some predictions. So let's say we want to make a prediction for a chicken sandwich that has 31 grams of protein. So I'm going to take the 31, I'm going to substitute it into the equation in place of the protein variable and see what my prediction is. So I would predict the fat for that product would be 36.6 grams. The actual sandwich contains 22 grams. So we notice here we actually have an over prediction. And so our residual there is going to be negative, right? Because we actually take the actual minus the predicted. So again, here we have a negative residual. This point would, the actual point, the 22, would fall below the line. So when you were graphing it, you would graph 31, 22, and that would not fall on the line, it would fall below the line. So what are the conditions? We always have to check conditions. The line of best fit is also called the least squares line or the regression line, and we only use it to make predictions if the variables are quantitative, as we had in Chapter 6 for correlation, the relationship is straight enough, and there shouldn't be any outliers. So you're checking the same conditions, and again, it's important for you to make a scatter plot before you attempt to build the regression equation. Okay, let's do an example. We're going to look at a baseball runs problem, and this is in StatCrunch, and I'll pull it up for you in just a second. The question is there a relationship between the total runs in the season and the average attendance? So I'm going to go ahead and I'm going to go over to StatCrunch, and we're in Chapter 7, and it's called, find the name of the data set. Maybe it was in Chapter 6. No, I think it's in Chapter 7. I think it's the second inning, maybe. Wins in attendance. Here it is. So first thing we want to do, we want to look at the relationship between the total runs, which is here, and the attendance in the season. So what do we want to, first thing we need to think about is what's going to be X and what's going to be Y. So it would seem like the number of runs would be generating additional attendance. So as the team does better, they would have greater attendance. So I'm going to go ahead, actually I'm going to see if I can, I hope you can see this. I'm going to go ahead and do a scatter plot so we can take a look at this. Scatter plot, and I'm going to put runs along the x-axis and I'm going to put attendance along the y-axis, and let's just take a look at the scatter plot. Let me pull it over here. Okay, so there's the scatter plot. We notice it's got a positive direction, a somewhat linear form, probably moderate in terms of the strength, and there's nothing really unusual. There's not a lot of data points on there. Now, if we want to find a correlation, let's do a quick little review. We went to Stat, and we went to Summary Stats, Correlation, and we're going to pick the total runs and the attendance. And here's our correlation coefficient, 0.538, so again in the moderate range. Now, to do the regression equation, you're going to go to Stat, and you're going to go down to Regression, Simple Linear. You're going to pick your X variable, and we were using the total runs, and we're going to pick attendance for the Y variable. And for right now, that's all I'm going to select. I'm going to come back to this window in a minute, but let's just go ahead and get the regression equation. Okay, so here's my regression equation right here. So I can highlight it, highlight it for you right on this line here. There's the regression equation. It tells me in the window here that the dependent variable was the attendance, the independent variable was the runs, and then on the fourth line is the actual regression equation. Here's the y-intercept, here's the slope, here's the sample size, here's the correlation coefficient that we had just calculated. So this is pretty much the information. You're not going to use this bottom information here at this point. Let's go back over. And I've got all those windows in here. So there was the check of the conditions. And then we did the correlation. And then we did the linear regression, which you just saw in the window that I had open. So I can write the regression equation. Y hat is the attendance that we're trying to predict. Here's the y-intercept and here's the slope. So the slope tells us what? The slope tells us that every additional run on average is going to add about 54 people to the attendance. Correlation of 0.538 shows us that as the runs increase, attendance increases, which is what we would think. And again, there's the interpretation of the slope. The y-intercept here really doesn't have any meaning. This means if a team had no runs, they would have negative attendance, which doesn't make any sense. So in many contexts, the y-intercept won't have a real meaning. So we're looking at the residuals. Remember, the residuals are the difference between the y value of the data point and then the predicted y value that we find by solving the equation, substituting in that x value. To find the residual again, here's what you do. Get your y hat and then subtract it from the actual to find the residual. So the data that can be compared, here's one here on the maximum wind speed that we looked at before on the central pressure and the maximum wind speed. Hurricane Katrina's central pressure was 920 millibars, the maximum wind speed was 110 knots. So let's go ahead and do a prediction. So we're going to take the 920, substitute it into our equation, and we would have predicted a wind speed of 130.03. So what's the residual? The actual, the 110 minus, so it's about negative 20. So this model here was overestimating. Now, a good regression model, what you want to look at is some type of a residual plot. I like to do the residuals versus the x values. So let's go back over to the baseball example and pull that up. And that's why I said I would come back here in a minute. So if you go back into the options and you edit, and if you scroll your way down here, you're able to get different graphs right here. And so I like to do, one thing nice to do is a histogram of the residuals, and then also the residuals versus the x values. Those are the two graphs that I like to look at. And let's go ahead and take a look. You'll have to flip through the output. There's the, let me change that and show you one other thing. I also wanted to show you the actual fitted line plot. So let's go back for a second. So again, if I flip through here, here's the graph that we had, the scatter plot. There's the fitted line. All right, here's a histogram of the residuals. What you're looking for here is unimodal and symmetric. You don't want to see any bimodal or a real skewed distribution. And then this is a plot of the residuals versus the x values. And you don't want to see anything here. You want to see a random pattern because that tells us that our model has taken out the variation that's associated with the particular x value here. So you don't want to see a direction, you don't want to see a shape, you don't want to see any bends, you just want to see random scatter here. You don't want to see a curve pattern, you don't want to see what's called a fan where there's more variation here and then it gets tighter or the other way. You want to see a random pattern. And since the mean of the residuals is 0, the standard deviation of the residuals is a good measure of how small they are. And a good model will have an equal spread of residuals. So again, I showed you that histogram of the residuals. You want to see a nice unimodal plot here. No skewness, you want to have it nice, just like this, a normal distribution. So again, back to the baseball runs, I just showed you this. There was the histogram of the residuals, and then there was the residual plot we just looked at. And we really don't see anything going on here. We see a random pattern. Tampa Bay and Toronto have the largest negative residuals, which are right here. Remember, you can explore on those plots and identify those. Yankees in LA have the largest positive. Must be this one and this one, I guess. So you can compare the variation of y, what you're trying to predict, with the variation of the residuals. Remember that the residuals, if the correlation is -1 or +1, the residuals are all 0. There's a perfect fit there. The points all fall on the line. If the correlation is 0, then the regression line is horizontal through the mean. The variation of the residuals would be the same as the variation of the original y values, but we hope that our model has helped us to explain what's going on. And so we can use another statistic called R squared. And this tells us the amount of variation in the whatever we're trying to predict that's accounted for by the model or explained by the runs. And so if I go back to my output in StatCrunch and flip back, and you'll see this on the output right here. Here's your R squared for this problem. So it's about 29% for the baseball problem. The R squared is 29%. So that tells me 29% of the variation in the average attendance, what we're trying to predict, is accounted for or explained by the runs. But that also means 71% of the variation is still left there. There must be other factors that are affecting the attendance of the baseball game other than the number of runs. And they could be a lot of things. Last year's performance, who's playing on the team. I mean, there's a lot of other things. But R squared tells you the amount of variation accounted for in the y, the thing you're trying to predict, that is accounted for by the model or by the x variable. Either one of those is an acceptable interpretation. So it gives us a measure of how useful the regression line is as a prediction tool. If it's close to 1, we say that the residual is regression line is very useful. If it's close to 0, the regression line is not very useful. There's not really a criteria for how big R squared should be. It really depends on the situation. Similar to the R, when we looked at correlation last week, I couldn't really give you a fixed number that said strong or moderate or weak. But you always want to report your R squared when you're working on a regression model and let your researcher or your reader decide. Now remember the assumptions and conditions we talked about before. Quantitative variables, straight enough condition, no outliers. The other thing that we also look at is that the spread of the residuals or the data should not change as the x values change. It should be constant. And so if you take a look at a plot like this right here, there should be no bends, there should be no outliers, there should be no changes in the spread from one part of the plot to another. So let's take a look at another example here. This is sugar and calories. And we're going to look at the scatter plot first. And we see as the sugar increases, it looks like the calories are increasing. So somewhat positive direction. Somewhat linear, fairly, I would say, moderate to strong. No real unusual outliers. And so we wanted to determine what is the relationship between the sugar content and the calories in the cereal. Both variables are quantitative. Let's check our conditions. The scatter plot looks straight enough, and there's no obvious outliers. And the plot does not thicken. By that we mean if we look at the variation as we're moving across the x value. So basically you're saying for this value of 12, is the amount of variation I see here similar to an x value of 4 or an x value of 6. So again, you don't want to see a fan pattern with a lot of variation here and then the points get close together or vice versa. Okay, from StatCrunch, I'm not going to go back over, you could work on this yourself. I think you do have a data set for this one. The correlation was 0.564. Here's my regression equation. Here's my R squared. Now notice R, if you square it, you get R squared. There's your standard deviation on Y, and then there's standard deviation on your residuals. Notice that it's gone down, which is what we expect to see. When we fit the model, we take variation out of Y based on the fitting of the model. Okay, so the slope tells us that there's about 2.5 calories per gram of sugar on average. A serving of cereal has about 2.5 calories of sugar on average. The y-intercept predicts what sugar-free cereal would have about 89.5 calories in it. So R squared tells us 31.8% of the variation in calories is accounted for by the variation in the sugar. The standard deviation of the residuals, right here, is somewhat smaller than the standard deviation of the calorie that we're trying to predict, y. And again, here's a residual plot. I just see random pattern, which is what I want to see. I don't see any curves. I don't see any fan pattern. Equal scatter when I go from left to right, so it looks good. The linear model appears to be appropriate. Okay, reality check. When you're working a problem, you always want to think about whether or not the prediction is reasonable. Does it seem reasonable that a serving of cereal would have 2.5 calories for each additional gram of sugar? You might look at some boxes of cereal to see if that makes sense. Important to remember, correlation is not causation. We go back to that in Chapter 6. You can't report a cause and effect based solely on regression analysis. What can go wrong? You want to make the scatter plot first. You don't want to fit a straight line if the data is not linear. Don't ignore the outliers. Report them and then think twice about using the regression analysis. You might want to take them out look at the fit with and without. Don't invert the regression. By that I mean don't switch the position of x and y. Think about how the variables are related. You can't just solve the regression equation for x and then say that's another regression model. You'd have to refit. Okay, a couple problems to finish up with. Here's a least squares regression line that was calculated to relate the length of newborn boys to their weight in kilos. And explain what the model means. Okay, so this tells us the baby's weight increases by 0.8175 kilos for every additional centimeter of length. A newborn was 48 centimeters and weighed 3 kilos. What's his residual? Okay, so we're going to take his length and we're going to make a prediction first. And when I do that, I would predict that he would weigh 3.06 kilos. And then I'm going to calculate the residual. I'm going to take the actual, he weighed 3, and minus the predicted. And so the model is overestimating a little tiny bit because it's got a negative residual. Okay, one on alligators. Wildlife researchers monitor many wildlife populations by taking aerial photos. Can they estimate the weights of the alligators accurately from the air? Here's a regression analysis of the weight of the alligators and their length. Here's the y-intercept. Here's the slope. Here's the r-squared. Did the researchers select the appropriate variable for x? Explain your answer. So they're trying to predict the weight based on the length because it's easy to measure the length, say, by flying over in an airplane. And so that would make sense that they're going to use the length that they can estimate from the air easily in order to predict the weight. What's the correlation? Okay, so they only gave me r squared. I notice the slope is positive, so I can take the square root of r squared to get r. And I know it's positive because the slope is positive. And again, also in context, as length increases, weight will increase. Write the equation of the regression line. Okay, it's going to be y hat equals negative 393, that's the y-intercept, plus 5.9 times the length, where y hat is the predicted weight. Interpret the slope. So every time the length of the alligator goes up by 1 inch, the weight increases by 5.9 pounds. Do you think that this equation will allow scientists to make accurate predictions about alligators? Okay, there's a nice r squared there, but remember, we did not look at the scatter plot, so we couldn't examine it for linearity, and we didn't examine the residuals, so the assumption may not be valid. It's so critical for you to take a look at the scatter plot to assess the conditions before you try to make some conclusions based on statistical software output like this. So hopefully this will help you as you're working through your homework in Chapter 7.